Right, a very quick summary of where I've got up to, because I'm very proud of this, and I think if it could be developed, it could go places. Basically, this is one of the things that I produced as a consequence of doing a platonic solids project, inspired by Euclid's Elements of Geometry, a very old book with very traditional proofs in, a work of great renown, a real benchmark for mathematicians. But in it, Euclid lists 5 platonic solids and proves that there are just 5 platonic solids. That's in there. But I've discovered so much on my journey getting to here, I wanted to share it with everybody else. So I'll go into more detail as I go to each bit. This is not a platonic solid. So it sounds a bit contrary, but in fact there are subsets of the points on here that hold, that define each of the 5 platonic solids, and that's why I've included this. And not only that, but this shape is now cutting edge technology. If you look at quasi crystals on the net, you'll find that involves this thing, which is a triacontahedron. Triaconta is 30, and hedron is facing 30 faces, and all those faces are rhombuses. And a rhombus has 4 equal sides, but it doesn't have 4 equal angles, because that would be a square then. It has 2 acute angles and 2 obtuse, and the long diagonal and the short diagonal, and one is the ratio between those is what's called phi, 1.618 approximately. And in fact, that was one of the first things I did. I just got this out of the garage, which is why it's so lusty. You see all the rhombuses are clearly seen here. And inside, I put some diagrams on. I did all the obtuse angles in one colour, the acute angles in another. You find that all the acute angles always meet at the same at a vertex, where only acute angles meet, and all the obtuse angles, they always meet at a vertex where only obtuse angles meet. So each vertex is composed of either acute angles or obtuse angles. And if you follow the obtuse angle vertices, you'll get an icosahedron. So there's precise points that form an icosahedron, which is a platonic solid. And if you follow where all the obtuse angles meet, you get a pentagon, which leads to a dodecahedron, and that's a platonic solid. We'll see those in a second. Anyway, the other thing I did was, when I made the shapes, I didn't just make the shape and that was it. I made it so that we could open them up and see inside. And you'll see. That's what I've done here. And you'll see again, I've done inside this one, I've actually made the rhombuses very explicit. You can see them all here. I haven't colour coded the vertexes, but here, where I've got the string, that's where 5 acute angles meet. And another type of vertex is where 3 obtuse angles meet. And that's on here. And the rhombuses are here. The other thing I did, which led to this nice pattern, I think, is I took each side, went halfway along and did the perpendicular, and did that on each side, and I ended up with this. And there's all sorts of nice maths on there that you can go into. This one, the rhombuses are more explicit there, because I haven't taken it apart. It should slide together. They can only slide together because these rhombuses here are parallel to these rhombuses on this side, on the waistband. So they slide along each other because they're parallel to each other. Right, so I'll put that there. And inside this, we've got our first platonic solid. And this is made of equilateral triangles. Initially, it looks like this. Yes, see all the equilateral triangles here. But I wondered about putting a triangular window in each side. So here you can see that the next platonic shape, each vertex is in the middle of each triangle, and it shows you the specific points that they match up with. Let me take this off, this comes apart, and you see the way I achieve this. And they look like straws. I've done a sort of subframe. It looks like straws, but in fact what I did was I got cocktail sticks and I wrapped paper around them very tightly, then took the cocktail sticks out and it made these spars for me. Quite strong enough to hold it together. Being paper, they glue easily, and again, lots of maths we can do on this. Got 5 angles of 60 there. Okay, and there's equilateral triangles, and that's a platonic solid. Let me take that out, we'll look at this one in a second. Let's put this back. Some soccer balls, sometimes have this design made of equilateral triangles. Normally made of pentagons or hexagons these days. There's all variety going on. So that's the icosahedron. And that led to a dodecahedron. Dodec, do is 2, dec is 10, dodec 12. You add the 2. Dodecahedron, 12 faces, and they're all pentagons. I'll take the top off. You'll see, oops, this one back. I've still got the dodecahedron. I've got the 12 pentagon faces, but on each face, what's called a pentagram. Join the line. And again, lots of maths in there. Lots of maths. These 3 angles, although they don't look as if they're the same, they are, and they're all worth 36 degrees. 3 there, 3 there, 3 there. That's 9 angles to 36. What's that? 324. So 324 degrees at every vertex. And there's some interesting things we can look at on that. Some of the angles on a polyhedron. Very interesting results there. You'll see here, I've got another one, which looks the same, it's not. There's all sorts of options with these, lots of different ways of opening them up. Now inside this was supposed to be a cube, and I found it difficult to see where I get a cube out of that. This is one way. This just flips back. I put some duct tape on here to make a hinge. There's our cube. I think I've done that elsewhere. So I'll put this one. And on this one you can see I've shown where the square faces of the cube are. Okay, so this is the dodecahedron. I've extended this slightly so that it fits right. So still our dodecahedron. You'll see inside this, again I've used duct tape so that I can fit some of these. We have our cube. In fact, let me push it out. There we go. That's one way. Just discovered this way this week. In fact, what I've done, I won't spend too long, it's like I call this a rooftop. And there's 6, if I put a rooftop on each side of the cube, I end up with a dodecahedron, so that's the connection between the two. I'll go to this one. Now here's a different way. I discovered that I put two pentagons together onto a rooftop. I can take them all out. One, two, three, four, 6 rooftops, 2 pentagons on each rooftop. That's 12 pentagons altogether. And 12 pentagons form the dodecahedron. The 6 squares on this side give you the cube inside. And so I'm thrilled with that. I'm very proud of that. That's pretty good. Next, inside we have the cube. So far we've had the icosahedron, we've had the dodecahedron, this one with rooftops that flip up, this one with 6 congruent pieces, and this is the cube inside, and the cube again, I've done this with duct tape. Now this time we get a pyramid here. It's got 3 right angles at the top. These are 45, so this isn't a platonic solid, but it's seemed preferable to leave it in because it fills the cube up nicely. There's our cube. I call this a right angle pyramid because of these 3 rectangles. Got an equilateral triangle base there. It's got 4 bits that come up like that. There's 4 pyramids like that. And this thing comes out in the middle. There's 1, 2, 3, 4. Okay. Remember the cube. 1, 2, 3. One in the middle. 4 pyramids, triangular based, not square based like the Egyptian ones. Triangular based with 3 right angles at the top. There's 4 of those, and nestling in the middle of those is the next platonic shape, which is the tetrahedron. Tetra is 4, and Harry will explain this in a second. Here's my nephew, he's coming on next, and he'll show you how to look at that. And inside the tetrahedron, see I put some lines on each face here of the triangle actually. That's interesting. How far down did they all meet? Clearly this length is bigger than this one, so they're not the same there. The sides of the triangle are, but to that centre isn't. And what about well, I'll talk about that later. Now we open this up inside. There we go. We got this. And again, Harry will show you this. There we go. So we get a small tetrahedron, we get large tetrahedrons. Okay, that's the same type of platonic solid. Now we end up with this one as well. It's got 8 faces, and this is the octahedron. And Harry will show you how they all fit in. And I think any student who could make these, or the teacher had them, there's lots of material here. There's lots of good mathematical questions you can ask. Well, there's lots of interesting ways of opening them up. And it's been a really interesting journey for me. I found lots of interesting things about the platonic solids that I didn't know before. And it was just meant as a gentle introduction. I thought to myself, if they've been around for 2,500 to 3,000 years, then they'll have found out everything about them, but they haven't. And it leads on to all sorts of other interesting things. Yeah, I'm going to stop there. One thing I would like to know, if anybody's interested in this, I'm sure there's a market out there. Now, if anybody's interested in marketing these with me, then please contact me through the reference on the video at the end. Thank you.